Hello, everyone. Today's interview is with Jared Pollack. This was captured back in 2015. I apologize for the poor audio recording, as this at that time was just captured over a telephone call.
Good question. We were studying mussels, and not the kind you from the sea, not mussels. Actually, I once got a postdoc because he heard that we were working on mussels, and he thought it was the kind in the sea instead of the kind that you use to lift barbells. And it was a mistake, but it turned out really nice. We were studying mussels, and it came to me that something is weird because all the people studying mussels, they draw pictures and schema of all the proteins inside the mussel, so actin and myosin and the like, and they draw pictures of how those proteins might interact to produce force and motion. However, they omit the most abundant component of the mussel, and that's water. So, we're 2/3 water by volume, but if you think of it in terms of the fraction of molecules in our body, or in our muscles, or in our body in general, you need a lot to fill that 2/3 with water. The molecules are so small that you need a lot of them. So if you do the arithmetic, it turns out that more than 99% of our molecules, or the muscles molecules, are water molecules. And so it seems, it borders on arrogance to think that, you can omit 99% of the molecules and thereby you get the right answer. That seemed weird to me. And so I began thinking about the role of water in mussels. And I happened also to meet about that time a person, Gilbert Ling, and Ling is now 96 or 97 years old. And Gilbert had been studying water in cells. I happened to meet him at a conference somewhere, and I became really impressed by not only what he had contributed, but also a cadre of people who were kind of more or less following or supplying evidence to support his view that the water inside the cells, and that would include muscle cells, the water inside was not like the water in a glass of water, but ordered in some way. And so putting those two together, the Gilbert Ling's massive amounts of evidence and other people supporting that, and the idea that in muscles, how could you understand how muscles contract if you don't take into account all of the water that's inside the muscle? So those two brought me to kind of a deep interest in water and water structuring. So do you want to hear more, or we can stop there? Maybe that answers your question.
Yeah, that was your inspiration for your first book, Muscles and Molecules? Is that
yes and no. The first book, Muscles and Molecules, was written before I got really deeply involved in this, and that book was written in 1990, and it was just a little after I met Gilbert Ling, and I knew that water was important, and I think I touched on water a little bit in that book. But that book was mostly a challenge to the existing ideas and demonstrating that some kind of contraction of the proteins, unlike a sliding of the proteins, which is the current view, and involving water in some way, but it was not really completely developed at that point. That's where it started. Then the 2001 book, Cells, Gels, and the Engines of Life, which amazingly is still a lot of people are beginning to, or continue to purchase the book, and I guess they find it interesting. That one was really designed to show how important water is in all of biology, and that it was based on Gilbert Ling. In fact, it started as an attempt to, you might say, clarify or popularize or what have you the contribution of Gilbert Ling. And as I started writing, and I realized that Gilbert, was right on, and that there was more, and the more is actually that the role of the ordered water inside the cells was maybe beyond what I believe Gilbert had been talking about, and there is a more active role that when the ordered water undergoes a transition from order to disorder, a kind of phase transition. That phase transition was really the driving force for the actions of the most common cell actions that you can think of. For example, in the case of muscle, it's the initiation of contraction, going from rest to contraction, triggered by this kind of phase transition. For cell division, mitosis, again, the transition from ordered to disordered water was important. And for secretion, there had been a lot of evidence when the cell wants to spew out various hormones and the like. The initiating action is, again, a transition of the water from ordered to disordered. And I showed in that book that in so many instances, if you simply take account of the idea that the water in the relaxed cell, if you will, is ordered, and in the activated cell it gets disordered, you can explain so many basic phenomena in a really straightforward and easy way. And that was the essence of that book. And so it was then that we really, at 2001, that we really began studying the water. It was so clear that the water was so interesting in all biological processes that we felt compelled to find out more about it. And that's what started our research, which led to all the wonderful things that I think are happening now, and which led to the recent book called The Fourth Phase of Water. I hope that answers.
Can I ask you just, you just opened a question that I just want to straight out ask. Do you think water is intelligent?
Good question. I laugh because
it's a loaded question.
No, I don't. It's fine. I didn't mean that. But what I mean is that we could talk for hours on that very subject, and so I guess you can surmise from this my response that there's really a lot to say about it, and the answer is I believe yes. So the idea actually arose a long time ago, but the main proponent of this was 2 decades ago was Jacques Benveniste, who essentially lost his career because he put forth evidence that he thought was convincing that water contained some kind of information, and it was a real debacle that took place. Some arguments with the journal Nature, and finally they published his paper with a disclaimer that we're not really sure about this stuff, but we're going to send. You know the story, yeah. So we're going to send a committee of peers over to look over your shoulder, and blah blah blah. And so finally, the committee of peers turned out to be the editor himself, who was a physicist rather than a biologist, he dropped out before his PhD and became a journalist and rose high in the ranks to be the editor, but not someone who was versed in biology. And the second one was the amazing Randy, the magician. So kind of an odd person to send as a peer. And the third one was a fraud buster from the National Institutes of Health. Again, so it was pretty clear that they suspected fraud, and they went over there and they spent a few days, and even though 2 out of 3 of the experiments confirmed that what they reported was accurate. Actually, they reported that it doesn't always work, their experiment, but most of the time, easily enough to be statistically significant. But after one failure, in which the fraudbuster from NIH is the guy who did the dilutions that were underlying this memory idea, They got a negative result, and so they huddled in their hotel, and they decided that this was a trick, even though they couldn't identify what the trick was, and the idea of water memory then became a joke, a scientific joke. You know, you got something that's ridiculous, and oh yeah, remember water memory? It's probably something like that. So, unfortunately, that incident set the tone for the future, and water memory became something of a joke. And you know, one of the reasons why people resist even entertaining the idea that water could have memory, because we actually think of it as water as a whole bunch of molecules that are dancing around randomly at not microseconds or nanoseconds, but maybe femtoseconds. It's really a quick dance of randomly organized entities. And how could these random entities possibly store information? It just seems ridiculous, and I quite agree. However, what we discovered is that this structured or ordered water actually forms a kind of matrix. It's a structural matrix that's rather stable, and all of the molecules, the oxygens and hydrogens, are ordered in some three-dimensional array. And when you think of this three-dimensional array of oxygens and hydrogens, it's actually not so different from the three-dimensional array of a digital computer, which is silicon dioxide or molecules arranged in some three-dimensional array. And everybody knows that that array stores information. So it's not a far cry to presume that this structure of water that we identified has a similar capacity. And so I mean, that's from the theoretical point of view. So we start with the idea that the public presumes that water memory is absurd and ridiculous and impossible, and now the theoretical background suggests that, hey, you know, it might be possible. But the evidence now comes from many people. We organize the annual conference of physics, chemistry, and biology of water. And tell every year, and anybody who's interested, I think it's a great meeting, and Nobel laureates have come, and it's informal and fun. And this year it'll be held in Bulgaria, a seaside resort in October. But anyway, people come to this meeting and make presentations, and a substantial fraction of these presentations is involved with presentations of evidence for that water actually stores information. And some of these presentations are, you know, absolutely sound, full of excellent controls. And you know, if you stand back and forget the ambiance of that water memory is a big scientific joke, and just look at the evidence, you see that there's increasing rationale for this point of view. And so the bottom line is, this is not only plausible, but evidence suggested, and if true, it could be an amazing breakthrough in science, because we receive information all the time. You know, our bodies are filled with water. Most of the water inside our bodies is the structured kind. We call it EZ water or fourth phase water. And so it's entirely susceptible to the storage of information and actually the release of information as well. So I'm sorry, there's a long answer to your short question, but I think the short answer is yes.
Yeah, that was a good question, Ellie. Is there a process for structuring the water? Something that we can do, you know, before we drink it?
Well, many people claim so, and these claims have not been, well, how to put it, so far, it's hard to judge because, you know, for example, if you're selling some water and you say, well, this water is just full of positive information, and actually there are quite a few waters that claim that, and they say, well, we have tremendous evidence that it's good for your health. But the problem is that those claims are always clouded by perception that you know, it's possible that since this is a commercial organization, you know, the evidence may be tilted slightly in favor of the fact that it really is good for your health. I don't doubt it. It's just that from the perception, from the point of view of people out there, what really needs to be done is that these waters that are commercial waters, or even spring waters that some people claim to or sell and claim to use, they need to be tested comparatively by a third party or an organization to see if the claimed efficacy is really supported. I think in many cases it would be, because in some cases I've actually been witness to the so-called anecdotal evidence that has been produced, and it seems actually rather convincing, sometimes amazingly so. I've seen evidence for pathology reversal. For example, kidney, irreversible kidney pathology reversed in multiple cases, and the evidence that's been presented looks really convincing that that's the case. And so there are many like that, and whether the information in some of these cases, information that's put into the water either by electromagnetic energy or by exposing the water to certain crystals and such, that really needs to be evaluated. And I actually, if I may, I put on a plea that we want to do that. And we don't have any commercial interest in any waters, but we have some understanding of what's involved and what may be responsible for the positive effects of drinking some of that water. And we tried to get money from the government, National Institutes of Health and such, and it's really hard because those people, the researchers at these places are mostly kind of, how should I say, their interests are aligned with pharmaceutical agents, and if you want to test the effects of a drug on kidney pathology reversal, well, that's perfectly reasonable and okay. But if you want to test water, it seems to border on the ridiculous, because everybody knows that water is just H2O, and no matter what you do to it, it's just H2O, and therefore it's even ridiculous to even conceive of the idea that certain waters could be beneficial, and especially waters that contain information. That goes even beyond reason to even some people would say it's in the realm of pseudoscience, whatever that means, and so it's really hard to get past that barrier. And so, if any of your listeners are connected with people of means and who want to do something for humanity, it would be really helpful to obtain some funding to carry out a really serious study to compare the waters and see if those waters that are treated in certain ways or are imbued with information really are efficacious in treating disease. Wouldn't it be amazing if you're sick and you could just drink a certain water and that will really help you to get better? I think the evidence that I've seen, I think it may be possible.
Wow. Yeah, that would be fascinating.
During our prior interview, you said something about the Venturi effect. Am I wrong about that? Did you not bring up?
I don't think I did.
It didn't occur to me. Excuse me. It didn't occur to me what I thought you meant until I was looking at this little Vortex wine device that I purchased for my father-in-law, and he uses it to make his wine aerated, but I noticed that it creates a vortex effect, a very effective one. It makes a cute little sound too, and it oxygenates the water. And I started stealing his thingy and cleaning it out and making sure that there wasn't wine residue in it, and then using it to spin the water through over ice. Is there any suggestion maybe that might create a structured effect, oxygenating the water?
That's correct. So a lot of people have been interested in vortices, vortex, and it started with I don't know if it started with him, but Victor Schauberger has been the major proponent, and Schauberger was in his prime during that, just before World War II, and he studied water. He wasn't a scientist; he was a naturalist, which makes his books and his writings a bit difficult for people to read, because his language German. His language didn't speak in the terms that physicists and chemists would speak. So, but anyway, he noticed that the rivers he often saw these vortices in rivers, and he came to the conclusion, based on his observations and studies, that these vortices were one of the main that's not the right word, were the vortices were necessary to produce what he called living water, as opposed to dead water. Dead water is water that just sits there, and according to him, there was something about the vortexed water that differed from water that was not vortexed, and that spawned quite a bit of interest, and that interest is now mushrooming, because a lot of people, just like what you reported about the wine, a lot of people are interested in studying vortices, and the bottom line is, it's not clear what happens in vortices, even why these vortices form. In other words, the physics and the chemistry of vortex water is still pretty obscure, and then the idea is, well, okay, so if you do have vortex water, then what are there some effects that you can measure? Now, Schauberger claimed that the water that's vortex cooled, and we started studying it. We have some evidence for that, but it's not really conclusive evidence, just a hint that might be so. Another thing is that the vortex, the idea, what he called living water, should somehow be related to living or life and such. And our finding is that life absolutely requires this kind of structured, easy fourth phase water, which as I mentioned, this fills your cells. And so there's a suggestion that on the surface of the vortex is really easy fourth phase water, and we've been trying to test that, and we're not sure yet, but the tests are continuing. So the other point is the oxygen that you mentioned, to oxygenate the water. Well, we found that if you have just water sitting next to air, which is often the case, if you replace the air by oxygen, the air is only 18% oxygen. If you change it to 95% oxygen, that tends to build the fourth phase of water. So if you extrapolate from just standing water to water that's in a vortex, the surface of the vortex is constantly exposed to the air, and it's moving so rapidly and almost turbulently, although it's not really turbulent. So you can imagine that lots of air is going to get trapped, and so the usual interpretation of that is that it's air bubbles that are getting into the water. But I think it's also possible, for extrapolating from our experiments, that what that oxygen does is it builds easy water at the surface of that vortex, and so all of this is right now is not conclusive, but it looks probable that the vortex is doing a lot of interesting stuff, and following what Schauberger said, it's still not absolutely clear, but perhaps your winemaker is going in the right direction.
Yeah, okay. Well, let's move on to the next question. Dr. Pollack, why do you think it's important that the body, or the human body, absorbs sunlight, according to your theory?
Oh, okay. So, first of all, theory should be distinguished from experiment. There are lots of theories out there, but the theory is maybe as valid as all the assumptions that underlie the theory. And a lot of theories are okay or interesting. Some may even be right, and some may be non-starters. But sure, you might say theory, but our experimental evidence is that if you add light to water, the light, the energy from light, builds this easy water, fourth phase, structured water. And we have direct evidence for that. You just turn on the light and you can see it growing. You can see this zone. I should mention for those who are not familiar that usually this zone grows when water interfaces with some so-called hydrophilic surface. It's not every surface. It's the surfaces that hydrophilic water love water. Those kinds of surfaces, And when you have a surface, when you put it down horizontally and you put a drop of water on it, and the water spreads out. Most surfaces are like that to varying degrees. So essentially, when you have a surface or a material that's immersed in water, the surface or the interface where the water meets that surface, that's where the fourth phase grows, and it grows hugely. It's many, even millions of molecular layers. So it's pretty major. And so we have a chamber where we study this in a microscope, and it consists of a hydrophilic material next to water. And we can watch this zone growing under the microscope, and you watch it grow, and if you add light, it grows bigger. And we've seen, even with fairly weak light, we've seen it grow by a factor of 10 times, so reversibly. So it's pretty interesting, and we know that light builds this zone, and we even know which wavelengths of light are most responsible. So, extrapolating from that point of view to I guess, answer the question that maybe a lot of people are interested in, well, what happens about the light that is incident on your body? Well, what about sunshine and sunlight? So, of course, we're filled with water, and the water that we have, as I mentioned, is mostly EZ water inside our cells. And because the reason it's EZ water, I mean, we know from many pieces of evidence that most of the water in our cells is EZ water, but one way to think about this is the cell is like a matrix full of charged hydrophilic surfaces, just like proteins and nucleic acid. All the macromolecules are hydrophilic, and when they sit next to water, they build EZ water. And so your cell is filled with this matrix, and therefore all the water that's inside this matrix, most of this water, I shouldn't say all, is EZ water. Some people think all of it. I think most of it. So we know what happens when light hits EZ water, it builds more of it, and your cells need this kind of water to function well. So when you're born, you're, I guess, about 80% water. When you get to be a little bit long in the tooth, then you're down to maybe 60% water. So it keeps decreasing with time. And what we all need is hydration. So hydration amounts to the buildup of this EZ water. So getting back to your question. So what happens? Why do we need sunshine? So you walk out in the sun and you feel good. Particularly in Seattle, we have gray skies, and I know in Alaska you've got that too. And so when the sun peeps through, suddenly everybody feels good. So why do you feel good? Well, most of us think it's purely psychological, and maybe it is to some extent, but also the sunlight itself. We receive the sunlight and the electromagnetic energy, the sunshine. The light actually penetrates fairly deeply into our body, and so what does it do to the water in our body? Well, it builds EZ water, just as we found in the laboratory. So you go out in the sun, your EZ water builds up, and your cells are working better, especially or including those in your brain, and you feel good. And it's another example of this is in a sauna. So there you don't receive light, but you receive infrared light or infrared energy, the heat. It's pretty much the same as the sunlight or visible light because there's just a different wavelength. That's all. The visible range of wavelengths is from 400 to 800 nanometers, and then if it's more than 800, like 900 or 1,000 or 1,100, you're in the infrared region, and so the sauna provides infrared energy or infrared light to your body, and we found that the infrared light is the one that most profoundly builds this kind of water. You see, that's what we found in the laboratory. So probably the same is true in your body, that if you go into a sauna or a place with heat of some sort, you feel good, you feel better. And I recollect in Finland. They live on saunas over there, or with them, and in Russia, and where they call them banyas, and it's pretty much the same. You go in for 20 minutes or so, and you come out, and you feel like $1 million rubles, or rubles aren't worth too much these days, but $1 million, and why do you feel that way? Again, the presumption is, well, some kind of vague psychological effect, but I think it's more than that. I think it may be partly that, but it's a physical effect. It builds, we know from our experiments, that this builds easy water, and the cells need easy water to function properly. And if our muscles, for example, are not working well, they don't have as much easy water. You got muscle ache and muscle pain, and if you put yourself under the influence of heat or from sauna or anywhere, your muscles usually feel better. And I think the reason is that they build up the easy water. Your cells now can function properly, and you feel better. So it applies, I think, to every organ in your body. So sunshine, sauna, any of that kind of energy is good for you. And I know there are many kinds of light therapies, like laser therapies, using many different wavelengths. They all have positive effects, and now we understand why.
Yeah, that's really interesting.
Sorry, I have a delay. They have devices up here in tanning salons that are infrared beds. And I'm just in awe that somebody knew that before you. They literally stated that it was a different kind of. I remember walking through, because I have to tan in Alaska, like you mentioned. It is gray skies, and if I want to go to the lower 48 ever again, I have to have some immunity to the sun, because I'm one of those people that catch fire. Oh. And so I tan very, I have to go to the beds where it's the round bulbs, not the strip bulbs. It's kind of a hassle. And the reason being is that it's less UVB. UVB is what sears the skin and thickens it. UVA is what brings forth a little more, immunity and melanin. It's a slower process. And then they had these other beds. These other beds were the fountain of youth beds, they said. And I thought it was interesting because it was red light. It was infrared light. It was basically heat, infrared, and this vibration thing for cellulite. It was like this weird new age, superwoman device, or I guess guys went in there too. But it was supposed to fight seasonal affective disorder without creating a tanning effect per se.
Oh, I see.
But I remember it was literally a red in an infrared bed. I just thought that was amazing. Bed.
Well, it makes sense. Of course, it makes sense to avoid effects on your skin if possible, and avoiding those wavelengths. But I think the red and the infrared, so it's probably a combination of the visible and the longer wavelengths in the infrared. And as I mentioned, that if what happens in your body follows what happens in the laboratory, then these salons providing that light will build up all of the structured, easy fourth phase water, which you need for function. So the function is also in your head, and when you're depressed, we're not designed to be depressed. We're designed to feel stable and optimistic, and if we feel depressed, there's some deficiency. Something is going on in our head that, of course, nobody fully understands exactly what that is. We attribute it to, various hormones and neurotransmitters, deficiencies or whatever. But basically, we're not designed. Something's wrong. Something's not working properly. And so, according to this very simple hypothesis or theory, if you will, that we function best if we have the proper normal supply of water surrounding each protein, because the proteins function by folding or bending or whatever, and their normal state as they do this is the protein surrounded by some kind of ordered water. And if you don't have enough of it, then the protein can't fold or bend or do its thing properly. So you need to restore it to its optimum level in order for the cells to function properly. And I think that's what these lights that you're talking about, I suspect that's what they do. They in your brain especially, but probably all over your body as well. So the depression tends to diminish in the presence of it. I don't know if it's a permanent effect or a temporary effect, but I know certainly in the case of the sauna, I rarely get depressed, but I remember walking out of those multiple times and feeling just wonderful, happy, at peace with the world. It's really wonderful.
Yeah.
I guess the Alaskans need it as much as the Finns need it. You're both up pretty high latitudes, not so much sunlight.
Yeah, we're kind of famous for the psychological situation of our populace in terms of good and bad. There's a lot of creativity. There's a lot of free-spirited, powerful people that are willing to live with wood stoves. And my girlfriend has a banya. It's funny you mentioned that word. A lot of people look at me funny because they don't understand banya is just another way of saying sauna from another place.
Yeah, sure.
It's not a surprise to me that all the Nordic countries are running for the heat source. Sometimes it gets so cold here, even in the house, where the house itself is of a normal temperature. It's not like it's an outrageous, 68 degrees is 68 degrees, right? No.
Yeah.
If it's cold outside, you feel that cold past the barrier of your protective coating.
Is that right?
And meaning my hands and feet are always cold. If anybody's cold, I'm the suspect cold person. And so, I've since taken very seriously the issues of structured water, taking cayenne pepper pills, everything I can think of to augment my circulation and make sure I don't feel that icy chill. Because when it gets you, it gets you. And literally the wood stove is everybody's favorite place. The banyo is the hangout at night. It's when it gets cold up here, there's not much else. There's not an alternative. Arthritis starts to set in. I mean, that's where I went gold panning. Yeah. And having my hands in that water, even through gloves, it just affects your joints in a way that I think it calls your immune system to play. I don't know what, but it's really, really brutal. So I can see that if you're up here working hard, which is the Alaskan way historically, you have to do something to compensate to get your body's immune system back in order. Because just having your hands in those gloves, it was summertime, but it's running water, and it's icy running water. It's coming off glacier, and you're prospecting. So that's the hardest work I've ever done, and it demonstrated to me the necessity of a sauna or some sort of heat source. So it doesn't surprise me that. So you said infrared comes from heat, not necessarily light.
Well, I didn't say it exactly. It's a bit confusing, and actually, I address this in my book. That sometimes it gets confused because I think that the term heat and temperature, they're useful for describing pretty much what you're talking about, but they're not really good scientific terms because they're ambiguous, and the ambiguity is expressed just in exactly what you pointed out, the relationship between heat and infrared. They're kind of confused, and I think if you at least scientifically, for scientific understanding, avoid the terms heat and temperature, then you can begin to understand the primary variable, so we say, is electromagnetic energy. And so if that energy, and it comes in many, many different wavelengths, and it's just a small, narrow band of wavelengths that we can see, and we call that the visible wavelengths, and sometimes we refer to that as light. But light really encompasses all of those wavelengths, even the ones we can't see. So they're all the same. The only difference is different wavelengths. That's all. There's a giant spectrum, of which a small component is what we can see in the visible range. So when you go to the longer wavelengths, if the energy that we receive is of a longer wavelength, then we refer to those wavelengths as infrared wavelengths. You could call it Henry or Fred or whatever, but it's infrared wavelengths. And we perceive those wavelengths because it feels warm if we get them. Our sensors feel a kind of a sensation that we call warmth. And that usually is in the range of well beyond the longest wavelength of the visible. So the visible ends, the longest wavelength is about 800 nanometers. And when you go to 1,000 or 2,000, or then you begin there and the longer wavelengths to feel the sensation of warmth. So you call it heat or warmth, but so that's what I'm trying to explain. What I view as the distinction, and so when you have a fire or go to a sauna, you get a lot of these longer wavelengths plus the shorter ones. So a fire, for example, you feel the heat, so to speak, and that's because you're receiving infrared energy from the fire. You also see the fire, which means that you're receiving visible wavelengths from the fire. What you receive from the fire is a broad spectrum ranging from the visible all the way out into the infrared. I'm not sure, but there might be some shorter wavelengths too in the ultraviolet. I should know the answer to that, but I don't. So it's a broad range of wavelengths, and we found that all of those wavelengths can impact the water. But as I said, the most impacting we found in our studies is about 3,000 nanometers. It's well into the infrared region. So you receive those wavelengths and the shorter ones too. And all of these are good for building easy water. So I'm sorry, I forgot what the original question was, but I just wanted to explain about the heat and the infrared. They're kind of interchangeable, but sticking to the wavelengths that you receive is really helpful. And when you stick your hand into the icy water, what happens is that you don't get much of that, but you generate this kind of energy, and that energy just loves to go out into the icy water, you see, and so you're losing a lot of it. So you feel, instead of feeling the warmth of receiving the energy, you feel the coolness of giving out that energy. And you need to compensate for it, you say, by sitting next to the fire or sitting in a sauna or banya, what have you. Okay?
Yeah. Hey, Billy, did you have any questions?
Essentially recharging your battery, so to speak.
Yeah.
I'm really interested in the battery aspect. According to your discoveries, we find a charge separation on a body of water where we find a negative charge on the outer layer and a positive charge on the inner layer. Is that correct?
Yeah, right. So
have you found
you're talking about a body of water, right, rather than the fourth phase and such.
Right. Yeah. Do you consider that in any way responsible for surface tension?
Well, yeah. So let me two answers. First, the battery effect. So I didn't mention, but one of the prime findings that we have is that this fourth phase zone is generally negatively charged, and the water beyond that, H2O, has a lot of protons in it, and so it's positively charged. So it acts like a battery, and so you can actually extract electrical energy from it.
Would that charge be proportional to size?
Well, it could be. We don't have full evidence on that, but you'd think it would be. So if you have a bigger EZ, you'd probably have more negative charge, and correspondingly, you'd have more positive charge in the water beyond. So we have a device that we've built. It's kind of like a photovoltaic cell. It works on light, and it builds easy. It's light and water. It builds easy, and it separates charge. And if you put one electrode in the negative and one electrode in the positive, then you get electrical energy. You get current flow and voltage out of that, and it's powered by light. So if you have multiple cells running in parallel, and therefore, as you say, more easy, then you get more electrical energy out of it. But I think your question is, if you have one EZ and if it gets bigger, do you get more charge? And it's a really good question and a fundamental question. And my answer is probably yes, but we haven't really tested that yet precisely. It needs to be done.
It'd be interesting to find out, because at some point we'd have to expect electrolysis to take place and water to literally split at some point, wouldn't you suggest?
Yeah, well, I mean, see, I think though that we're actually the reverse of that. So what's going on? This is the best that we can surmise from the evidence. If you start with just water, H2O, and light hits the water, that what happens is just like in the first step of photosynthesis, the water splits into the negative and positive. So that is the OH minus and H plus. So when more and more of the water molecules split, the negatives build up. It's kind of like a brick wall building up. They all stick together and build up this huge zone of negativity, and all the positives, the H plus, are pushed out into the water beyond. So yeah, I mean, the whole process involves the splitting of water molecules into plus and minus. But when you think of electrolysis, you're thinking of what happens when you actively put electrodes into the water and then actively split the water molecules. In our case, it's not driven by these electrodes, it's driven by light. So the light is absorbed by the water, and every water molecule that's split into plus and minus, and that's how the charge separation occurs, by the minuses getting together and building this wall of EV. So yeah, it relates directly to the idea of hydrolysis.
That's incredible. It's incredible. Well, we did a lot of research with the suspicious observers over the years, and we have what we call the Star Water series. I don't know if you're familiar with that.
No, I'm not. I know I should be, but
yeah, we found, well, a lot of articles have been posted over the years about water coming from sunspots on our sun, actually noted water coming from other stars, water shooting like jets out of the polar regions of some stars, and most of the time these are either new or dying stars that they observe this on. However, again, they've actually measured water vapor coming from sunspots. And so this, brings up the question in some, in an electric universe situation, could this star actually be made of salt water?
Well, that's a really interesting idea. I know that water is found more and more everywhere. There was just something in the New York Times yesterday about more and more water found on moons.
Yes.
Yeah. So it looks like water is well, so to speak, universal. Yeah. And I can't really answer to that except that I remember chatting with Don Scott, who wrote the book. Yeah. What is it called? The Electric Sun, I think, or something like that.
Sky, yeah.
Yeah, and when he saw our pictures of the mosaics that occur on the surface of water that are made by some sort of arrangement of structured and unstructured water, these cells, he said, the same thing appears in the sun, and he was struck by that. In fact, he told me he couldn't sleep the next night because it made such an impression on him. So I haven't thought about this a whole lot, but I think you might be onto something really important in that idea. That might be just full of water.
It very well be. I know a lot of discoveries about water in our own planet in recent years have been discovered.
Oh, sure. Yeah. The problem with the sun is that it's not so easy to get there to make measurements.
Yeah, that's the problem.
Yeah. Maybe one day you guys will figure it out.
Well, thanks very much. I enjoyed your answer.
Okay.
Sure.
So, Dr. Pollack, do you believe that water may hold the answer to solving many of our energy issues if we just understood it better?
Yeah, I do. As I mentioned, you can get energy from water by exploiting the potential difference. The EZ is negative, and the water beyond is positive. So where does that energy come from? Well, it's free. It comes from the sun, basically, and the infrared energy, particularly, which is particularly effective. That's all over the place. Most people don't really understand infrared energy. We think, well, if you have an electric range and you turn it on, it glows red, and that's infrared. And that's true. It generates electromagnetic energy, which includes a lot of infrared wavelengths. That's correct. However, it's not the only place where you find it. I like to give the example of turning off all the lights and shutting the shades, and the room is black and you can't see anything, and you whip out your infrared camera, which detects not the visible light, but the infrared light. And as you know, you get a beautiful picture of everything around you. And the only conclusion you can draw from that is everything is generating infrared energy. And it's true that the walls, the sofa, and the rug, and they're all generating infrared energy. And that's the energy that builds this kind of water. So we learn in chemistry book about free energy, but this is literally free energy. It doesn't really require a lot of understanding of the subtleties of chemistry. It's just there. It's there all the time. It's free. You don't have to pay for it, and it comes from the environment. So this is one example of many where you're taking the energy from the environment and turning it into useful energy. So this is the future. I think undoubtedly you and I have heard of many attempts to extract this kind of energy and use it. And so I think this is clearly the future of learning exactly how to tap this energy. Just one interesting example, just thought of is, a lot of people don't realize it, but the Earth bears negative charge, and the atmosphere above bears positive charge. So it's a very interesting couple of plus and minus. And of course, with that electric field that you get from the plus to the minus, you ought to think that, well, you can get energy from that because it's like a capacitor or like a battery of plus and minus. And people have done that starting many, many years ago. If you measure the potential difference, for example, if you're standing up, you're let's say a 2-meter high person, as the great physicist Richard Feynman pointed out, you put an electrode on your nose and one on your toes, and you got 200 volts. Well, so if you think of putting one on the ground and one, say, 10,000 feet up, you got a big potential difference. And people have exploited that. They put an electrode up high using a balloon, and another one down low, and so you have a huge potential difference. And you connect those two terminals to a motor, a regular mechanical motor, the older kind that used to run on high voltage and low current instead of the modern ones that do the opposite. You can drive these motors just from that potential difference coming from the environment and get real mechanical power out of that of very substantial means. We don't somehow exploit this. It's kind of it's kind of odd that you don't. You see wind farms and you see about the ocean waves generated, but there are fewer attempts that have become popular for some reason of exploiting the energy from the environment. I think that's the future.
I'd agree. I know a guy personally on YouTube that's actually done that experiment with he calls it the Atmo motor. He 3D printed, designed a little small, high voltage, low amperage motor that runs off of a wire he takes up with a drone. He just drags the wire up into the atmosphere with a drone.
Oh yeah,
and
sure.
He connects a grounding rod to it. It's in a little flask outside there. The only problem is weather. In bad weather, you're susceptible to lightning strikes when you.
Well, also in that case, I mean, the principle is demonstrated, but the energy to fly the drone is another. But balloons also.
Balloons. Good idea.
Have worked. There's actually a patent. I have a slide of it from I think 1919 or something like this, where someone actually used the balloon or a few balloons. He had a big hoop, a wire, and the wire was held up. I don't know how high it was, with a bunch of balloons and a very fine wire extending from that conducting hoop all the way down. And so as long as the hoop remained suspended from the balloons, he could actually power the motor. And someone reported up to, I think, like 75 mechanical watts, and that's a lot of energy, mechanical energy. So it's pretty substantial.
Yeah, in my opinion, aerial antennas could be reworked, and isolated to work in that, just in a stationary position.
I think that could be,
if
sure.
Isolate it properly and do it properly, yeah.
Yeah, there's a lot of energy out there, and there are a lot of clever people, but I don't know. It seems that somehow this is not progressing as rapidly as you would expect it to be progressing. Perhaps there are political or economic reasons why this is not moving ahead as rapidly as one might expect.
There's one company that gets passed around a few times with the Thunderbolts group, and it's called Blacklight Power.
I don't know that.
They're a U.S. corporation or company here, and they're working on that type of energy as we speak. In fact, one of the forms they use now is electrolysis. They create electrolysis, and when the gases are ignited, they produce light that is so many more times intense than sunlight. And so what they're trying to do now is create a photovoltaic cell that can handle that light, which would be equivalent to several hundred cells, just because of the intensity of the light. And
well, that's impressive.
But blacklight, I've heard. I've heard a bunch of people from the Thunderbolts talk about them, so maybe they're promising. We'll see what happens with them.
The company is called Black Light or Black Ice. I didn't hear.
Yeah, Black Light Power. Yeah.
Black Light Power. Okay, thanks.
Yeah, we just have probably one more question here, Dr. Pollack, and then we'll go ahead and wrap up. So, I guess with this fourth phase of water, would we consider this like the catalyst for life itself?
What do you mean by catalyst for life?
Kind of without it, we wouldn't have life.
Oh, yeah. Well, sure. I mean, it's so fundamental, as was just discussed. It might be on the stars, and it's in the moons and the planets and water. So water is so central for everything. And we used to think that we have three phases of water. The solid and liquid and vapor. But this fourth phase, I think, is really the most interesting one because I believe it is the as you say, catalyst for life. It takes energy from the environment and converts it to the kind of energy that we can use, and we do use in our bodies. So I think most people who study biology and biochemistry think that the ATP, adenosine triphosphate, is the supplier of energy of life. It's a kind of common denominator of energy, and there's actually evidence against that, but it's not popularly circulated. I think it's possible that the energy for life is actually, you might call it qi if you were Chinese, is actually the water that becomes the EZ water and separates charge. So you have a whole bank of negative charge and positive charge, and this electrical energy is used to run everything in our bodies. I believe that that's the case. So from that point of view, it makes sense when you say that this water is the catalyst of life, or easy water is the catalyst of life. I believe that that's correct. And if you think about a long time ago about the origin of life, we can imagine that long ago that we had the earth, we had water, we had sunlight. And we don't know what else there was. Sometimes I feel old enough that I might have been there, but we don't know what there was. But there's one principle, one central organizing principle that, and this is described in my book. It's a little hard to do this on an interview, but light brings particles together. It condenses them, and just try to describe how this works is that any particles that you have suspended in water, they build this zone around them, this EZ, and it has negative charge. And so you can imagine a lot of these particles or molecules scattered widely about, each one having a shell of negative EZ water. And so when you have these negative shells of EZ water dispersed throughout, in between them are positive charges. Well, we have a lot of evidence, it's presented in the book, that what happens is these intervening positive charges between the negative shells, they draw together those negative shells and condense them. So what happens is that when you have scattered particles to begin with in water, or molecules in water, you add light, they come together. They come together very naturally. So the principle is known as like likes like, and this was coined by Richard Feynman, the great physicist. He said, well, they're like charges. You have molecules, particles with same charge, but they come together paradoxically. And he said the reason they come together is, he said, likes like, they like each other, they come together. Likes like because of an intermediate of unlike. You see, and so he knew, and many people knew even before him, it's been known for 100 years, that you put some like-charged particles in the water, and they come together. Instead, you'd expect that they would be repelled, but they paradoxically come together. So if you go back to the origins of life and think that, well, we don't know what molecules or particles or what have you there were. You can speculate, but we don't know. But inevitably, if this principle holds, all you need is light, water, particles, or molecules, and that light, effectively, which separates the charge, separates negative and positive, creates the positives between the negatives, will bring them together. And once they come together, condensing into a pre-cell or gel-like colloidal particle, then you have the basis of a cell. Because you can't have a cell if the constituents of a cell or pre-cell are widely dispersed. You have nothing. You need them to come together to form life. And if this principle holds, then actually the first step in life could be occurring now, in every little pond that you can look at. It's just that the subsequent steps maybe are not being followed all the time, but maybe they are. So the bottom line of all this, when you say water is a catalyst for life, yeah, this is a kind of catalyst. I think that initiates. You don't need anything special, like the stars are just in the right place, and a magical set of circumstances showed up, and they were sufficient to create life. I think that's not correct. I think that life could have begun, and maybe is beginning, very simply, just from the effects of light and water, and therefore if true, the extrapolation from that is that there might be a lot of life out there.
Yeah, I would agree. Billy had done some experiments where he was showing algae formation using just light. You want to talk a little bit about that, Billy?
Well, no, that was actually using 12-volt batteries, electric water.
Nice.
Scientists have done the same test with what they call Tholin, where they take electricity and several different compounds, methane, for instance, or any other type of water-based compound, and they, create this brownish mud they call Tholin, which is an organic material. It's not biological, but it's the beginning of organics.
That's
just
really
by
interesting.
using electricity and water, basically.
Yeah, well, I think electricity is undervalued. We're basically electric beings.
Yes.
We all know the book Body Electric, which is in its 45th printing or something like that. And yeah, we're electric, and there's so much electricity out there. And my opinion, just like many of the people I know in the electric universe, is electricity is central for everything. It's so grossly underestimated, and I think that this underestimation has has really serious consequences. I think a lot of people have missed the central basis of charge and electricity and how they play out. And I think this has led to a lot of misunderstandings of nature. It needs to be reversed.
Yeah, I agree.
Yeah.
All right, Billy, Allie, did you guys have anything else you want to add before we wrap it up? Final questions or comments?
We appreciate your time.
I do have a quick is there a way that curriculum in general for sciences, and what I mean is what you've talked about today is essentially a blatant disregard for very obvious and easily harvested forces of energy that we can observe. So every single level of every kind of engineering or chemistry or science or just pretty much anything before anybody's allowed to go to any science class, they need to understand the nature of the environment they're standing in. Does that make sense? And I'm wondering, how can we affect curriculum as a whole to make everybody aware that, wait a minute, okay, you're studying solar energy. That's super. We want you to take this as far and out of the box as possible. But first, let's talk about what's right here under our nose. The tools you have to work with.
That's a powerful idea. I mean, that's a wonderful, wonderful idea. I think, the problem is that the problem starts with the teachers and professors and such. So being a professor at a university, I kind of understand the issue is that, the students are treated like empty vessels that need to be filled with facts. And so what facts do they need to be filled with? Well, you and I share a view on those facts that the students need to be educated about. But for most people who present the courses, it's really tough to stand up there and you're the supposed expert, and then if you really don't understand deeply what you're talking about, is a potential embarrassment because the students will ask questions that you can't answer. So you have to feel a real sense of confidence about what you're dealing, what you're talking about, and so there aren't too many people who are in that situation, and we're judged on what the students think and believe, or think of how we've conducted our class. And so there's a lot of fear out there of even among those who are really kind of beginning to understand or do understand much about the environment, which differs greatly from what we're taught. It's precarious to stand up in front of a classroom and teach this stuff. But it needs to be done. I'm totally with you, and I must say I just gave the last lecture 2 days ago in my class, and my class does just that. These are young students, freshmen and sophomores at university, and I present to them a whole lot of different points of view and explain the evidence for these points of view. And I think they come out of this with a new appreciation, not only for the evidence for differing points of view, but for the process itself of bringing forth fresh evidence that doesn't agree with the mainstream. If you guys can figure out a method of doing this, it would be phenomenal, because I think most of the students, they think that what the professor and the textbook tell them is truth. It's ground truth, and there's no reason to doubt any of it. And if we perpetuate this, this is a lost cause, because it's the young people that we want to educate. So one thing that we're doing, which may to some extent answer your question, we have a new organization called the Institute for Venture Science, and it's ivsci.org. And what we're trying to do is basically change the culture. And what specifically we're trying to do is to have an organization that will fund promising ideas that challenge conventional thinking. We don't have any money yet, but we're just developing this, and we have some ideas on how to get it funded. And so this, we think, we have a mechanism whose details I can provide, or it's on the website, which I think can be really effective in in showing not only promoting unconventional ideas that have real merit, but demonstrating that this is a really important thing that we need to do, because there have been so few fundamental scientific breakthroughs in the past decades. You can count them on your fingertips. Plenty of technological breakthroughs, but fundamental scientific breakthroughs are really hard to identify. We need them. We want them. And so if we can be successful in the next few years, I think this will be a kind of demonstration that begins to change the culture, a culture that now is the students learn, and this is well known. There's no reason to challenge it. To a culture where challenging or pressing the proponents to really prove their point. If not, let's think differently. This is what needs to happen. So we're starting to do, in answer to your question, how can we do this? We're starting to do it. There may be other ways to launch some educational programs. There are many people who espouse differing points of view in many different scientific fields. I know a lot of them myself, and one idea is for some of you people who are deeply into this is to gather together, huddle, and figure out who the most interesting of those people are, put them together, and suggest a kind of curriculum for young students. You could do it on the web, for example. Rupert Sheldrake and his colleagues have something called Open Science Forum. They're on the web. They just started it, where they're bringing together many of these ideas. So somebody proposing either at the elementary school level or high school level or university level to kind of put together a course that's built of some of this material, it would be wonderful. A great idea, I think.
You know, I did a documentary where I heard a quote discussing the architecture program for Virginia Tech, and we were doing a 50-year retrospective history of their program. And one of the engineers interviewed said something that it actually shattered my illusions. It made the ground I was standing on shake. He said, "We taught our students how to think." What an idea! And
what an idea!
Being sarcastic, but he was right. What they did with the program was they brought a Swiss architect over who had done the Ivy League dotting, in the United States, and everybody was fighting for him. And he wound up settling at Virginia Tech and creating a program where they taught students how to think, how to argue. He literally stated that it wasn't really a good class unless there was some sort of dissension in the ranks, and there was pressure put on them for that reason.
Was that Henry Bauer who did that?
Let me see. No, it was. Oh boy, Lucy and his wife was Lucy Ferrari. Lucy Ferrari was his wife, and I'm trying to think of his name. I apologize. He was the program leader. But it was the quote that stood out of one of his colleagues that, described what it was that he tried to do there. It wasn't so much a question of teaching architecture. That's why they were one of the first architecture programs to bring building construction and the art department into the same building with open walls. And they wanted people's work sitting out on the desk to be critiqued by other students. And they wanted to create this situation of sharing and cross-cultural sharing of knowledge. And their program is pretty amazing. I wanted to just pitch it all and go there. Every time I do a documentary on some new program, I'm like, oh my goodness, I got to go there. But, you only got one life. You got to slow it down. But they were teaching their students how to think. And I think, so this isn't exactly curriculum that hasn't already been written.
Yeah, there's another example of that I just came into contact with. I gave a talk in Vancouver at the Boucher Institute, which is a college or university or whatever that teaches alternative medicine, and there I met the dean, who also teaches a course in thinking, how to think, and he was detailing the methodologies that he uses, And well, gee, it's it's really amazing what the exercises that he goes through. So I could connect you with him later if that's of interest. But you know, these varied examples that you're citing put together some of the materials that these people use into a curriculum that could be, you know, I'm sure that each one has a few variants that maybe not only specific to their presentation, but could be really effective in putting some of these ideas together and somehow creating a course that's generally useful would be just amazing. I think a lot of people would adopt it because they're often looking for something that's new and exciting and something they believe in and something that they don't have to actually be responsible for teaching. You can just show the video, and a series like that would be spectacular.
Yeah, few people want to be the lead dog on certain things. And I just remembered, his name is Olivio Ferrari.
Oh, okay, Olivio. Now, Henry Bauer used to be the dean over there, and he's a really open-minded kind of fellow who believes in alternative. He's now retired, but still quite active, and he'd be someone who'd be interested, I think, in this general category of having people think or teaching them to think. I mean, that used to be characteristic of the Greeks, their educational system, and to some extent, I think the Romans too. And but it's disappeared. It's almost completely absent in modern curricula. Yeah. You know, it's getting worse because the humanities are being squeezed out, and because universities are now increasingly supported by industry, and they want engineering and practical stuff like that. So at least at University of Washington, the humanities are taking an increasing hit, and with that, the kinds of classroom activities that involve thinking, like as you say, philosophy and such, they're fewer and far between. I remember one famous scientist writing an article about this, saying that not one of his science courses taught him how to think.